Good day, class. Mr. Armkey back with you again for CTI 120. Today we're going to be talking about Chapter 8, Subnets and VLANs. Our objectives for today are to talk about the purposes of network segmentation, calculate and implement some subnets, and talk about how VLANs work and how they're used. So let's take a look at segmentation first. When a network is broken up into smaller multiple networks, traffic on one network is then separated from another, and each network has its own broadcast domain. Now, segmentation accomplishes three primary things. We can enhance security, improve performance, and simplify troubleshooting. So when we have a security enhancement, this is in order to separate traffic, as we said a little bit ago, to be able to ensure that something that belongs to one network that maybe has some privileged information isn't going to have the bleed over that we might worry about otherwise with a packet sniffer or some other potentially dangerous piece of malware present on the network. We're also going to be able to improve performance because, as we said, each network now has its own broadcast domain, meaning that a broadcast flood in order to discover a new device or something similar is not going to have the same drain on bandwidth. Now, networks are commonly segmented according to one of the following three groupings. A lot of threes today. Geographic locations, of course, where they're physically located. Departmental boundaries, so if somebody's in sales versus marketing or HR or the executive division. And then device types. We may have all of our switches on one grouping. We may have all of our printers on one grouping, running everything through a print server that can cross multiple VLANs. So here's an example. A business has grown from 20 or 30 computers to having a few hundred. Pretty significant growth, right? Now currently there's only one LAN or broadcast domain, and one router serves as the primary default gateway for the entire network. So that is the main means by which data enters or exits from our local network, right? That's what a default gateway means. Now, to better manage our network traffic, let's go ahead and segment the network so that each floor contains one LAN or broadcast domain. In order to do that, we're going to install a router on each floor and then configure the clients on each subnet so that they know which devices are their neighbors. Now, neighbors is predominantly a term that we use on IPv6, usually when we're talking about what's called link local nodes. But it is not a bad idea to express the idea of who belongs on a subnet with others of the same group in IPv4. So in this case, we're going to break it into three floors, so three groups or subnets. So here's figure 8.2. This is showing our previous situation where we had a switch for each floor rather than a router. So everything is funneling up to the primary router going out to the net. Not the most efficient. This is a little bit better structured. So now we have a separate subnet for each floor, and we have a separate router for each floor. So traffic control can be done not only at the floor level, but at the company level. So the router receives much more streamlined traffic. Now, an IPv4 address, as we know, is divided into two parts, what's called our network ID and our host ID. We use what's called a subnet mask to determine which part of an IP address is network and which part is host. The number of ones in the subnet mask determine the number of bits in the IP address that belong to the network ID. So let's take a look at a small example here. If we have the IP address 192.168.123.132 in binary, this is our representation. The subnet mask is going to be a string of ones traditionally based on what's called a classful division. So a classful division means we're going to divide it on the lines that would define a class A, B, or C IP address. So 8 bits, 16 bits, or 24 bits, meaning that the entire octet is going to be full of ones. So in this case, we're using a /24, which means that when we look at this, if we're saying that the subnet mask is going to identify the network portion by where all the ones are placed, then we know that the first three octets are going to be the network ID. So in this case, 192.168.123. And whatever's left over, by elimination, must be the host portion, 132. Now that's a pretty simple way to look at it if we're looking at a classful division, again, that 8, 16, or 24-bit boundary. So here's an example of what this table would look like for each of those masks. Now something we're going to talk about a little bit later on is how we can do what's called a classless subnet division. And this usually implements what we call VLSM. But first, we're going to talk about what's called CIDR, classless interdomain routing. So CIDR is a notation method of showing the network and host information in the IP address. So we can reflect the number of ones in the subnet mask by a single number following a slash. So in this case, 192.168.89.127/24 says that we have an IP address that contains a 24-bit subnet mask. So that means that our network ID in this case will be 192.168.89, and our host ID is 127. This is what's known as a CIDR block. Now, subnetting, as I said, alters the rules of classical IPv4 addressing. We borrow bits that would represent host information and instead use them to represent network information. So we're going to increase the number of what we call network bits and reduce the number of host bits. So the number of bits available for the network ID would increase. Let's say we just borrow one bit. A /24 CIDR block would become a /25. Now that first bit in the last octet would be used to represent part of the network. So let's go ahead and take a look at an example calculation. In table 8.4, we have the steps to divide IP addresses for network 192.168.89 into two subnets. So here we're going to do our host bit borrow, if you will. Excuse me. So we've got our binary representation, 192.168.89.0. Let's go ahead and determine our subnet mask. Okay, so we've got 255.255.255.128. We now know that that's going to be part of our subnet mask, as opposed to the previous /24 division, which would have been 255.255.255.0, what we call a triple max subnet mask, or a class C subnet mask. In step 3, now we're going to determine our network IDs, because the network ID is going to be defined by the subnet mask. So the network is either going to be 192.168.89.0, as it was previously, but that's only the first network. Now we've got a second network to where we have 192.168.89.128. So what we've done is, because we borrowed one bit here at the very front, we're now saying that that can be a simple 1 or 0 representation for the network. So we've cut the group of hosts for this subnet previously in half. So where we would previously have had 256 individual addresses, now we only have 128. And that magic number method, which you can look up later on, will tell us what our starter for the network should be. If we were to borrow 2 host bits, that would put us at a 64 address division for each. So our network, instead of starting at 128 for the second piece, would be at 64. And then we would have 128, 224, and that would be those would be our starters. If we were to do 3 bits, obviously we keep dividing down. Instead of 64-bit addresses, then we have 32, then we have 16, and so on. We'll look at a table for that in just a moment. So with our current address settings, we now have 192.168.89.0 as our first network. Its first host has to be the .1, the first address following the network ID. And the last host is going to be 126. It cannot be 127 because that must be reserved for the broadcast address. Something you must remember, no matter how small you cut a subnet, you have to still leave room for the broadcast and network IDs at the top and bottom, your first and last address in the range. Your first and last host address have to be inside of that secondary measurement. We see here also the network ID for subnet 2 is 128, so the first host must be 129. And the broadcast would normally be 255, so the last host must be 254. Now class A, B, and C networks can be subnetted, and every class is going to have a different number of host information bits based on the length of their mask. So let's take a look at 2 slides to show variations on this theme, class B and class C subnetting. So let's look at 8.6 first. Here we can see a standard list of class B subnet masks. If we're using, working our way up from a /16, which would be a class B division, we go to class 17, 18, 19, 20, and so on. So when we get to a 17, we now have 2 subnets. Each of them are able to support 32,766. That is half of the previous 65,536 that we would have had. 34, excuse me, because remember we have to reserve 2 hosts. Now if we get down to 24, which is a class C division, we see that it's 256 subnets with 254 hosts each. So that does not change. As we move down to 25, 26, 27, and so on, we see that the number of networks doubles and the number of hosts gets cut in half. And it doesn't seem entirely linear unless you remember each of the numbers in the far right column should have an additional 2. So 8,192, 4,096, 2048, 1024, 512, and so on. You'll notice that these subnet masks for the Class Cs are pretty close to what we saw before, but instead we're starting at the /25. So our number of subnets and number of hosts is going to change a little bit. But again, it's because we're counting how many bits we're borrowing from the division line. So if we're doing a Class B and we're borrowing down to /25, that's going to give us a different result than it would be of a Class C borrowing to a /25. Now we're likely to see two types of calculation problems for subnets. Given a certain number of network requirements, such as a number of hosts or subnets, we need to calculate the possible subnets as well as the host IP address ranges. The second type of problem would be, given an IP address, what is its network ID, what is its broadcast address, and what are the first and last host addresses that it belongs to. So here we see the subnets from the previous figure, 8.3, updated to now show their IP addresses. We can see router A is just our standard default gateway. Each of these routers here, if we look at router D, that's 89.1, router C is 89.33, and router B is 89.65. So that tells me that there is a 32 address interval between each. So we've broken down the original 256 addresses per to 32 addresses per. So we can see the network ID reflecting that 89.0, 89.32, 89.64. So we're now using a /27 mask as opposed to a /24. Now, why would we want to use a /27 when we could just as easily have gone in and done a /26? Well, part of it comes down to avoiding waste. Here we can see 6 smaller networks being subdivided out as well, but we don't see a difference in what our previous section was of .0, .32, .64, .96, 128, and so on. So we were able to do 6 networks with the same division that we used for 3. So by using a centralized DHCP server, usually from our first router, our primary default gateway, we can actually use a DHCP relay agent to make sure that every subnet assigns IP addresses efficiently. Now here's where the avoidance of waste comes in. VLSM, variable length subnet masking. This allows a subnet to be broken into further smaller groupings until each subnet is about the same size as the needed space. So this is often referred to as subnetting a subnet, subdividing a division. Okay? So to create VLSM, we're going to create the largest subnet first, and then we're going to break it down into the next largest, and so on. So what we can see here is that in figure 8.10, sales takes up about half of our address space, accounting takes up a quarter, and then we have an 1/8 for HR, and a 1/16 each for IT and executive networks. Now, what we can actually do to make things a little bit more efficient is squeeze it down like this. Let's say that for sales, we need 120 hosts. For accounting, we need 58. For HR, we need 25. For IT, we need 6. Executives, we need 5. And we need 2 groups of 2 each for the WAN links that will allow us to connect between external networks. So what we look at here is the number of hosts that's required, and we say, okay, what's the closest power of 2 that can be used without going under? So we don't want to go short, we want to go just over. We want to have a little bit of overage, but not an entire amount of overage. So if you remember from the previous slide, the subnets were calculated so that all of them were used. But we actually have a subsection here you can see in the /29 group that is unused in the gray. So 120 is close to 128, 58 is close to 64, 25 is close to 32, 6 is close to 8, 5 is close to 8, and 2 are both right dead on the money as far as powers of 2 to the first, obviously. So that's how we break it down. we go and figure out, okay, 128 hosts means that we will need to cover about half of what would have been 256. So we just borrow the 1 bit, and that allows us to have that 128. So remember, borrowing 1 bit means that's a representation of 128. If you have 1 followed by 7 zeros, that's 128 in binary. And that allows us to give us our magic bullet there. Let's skip down to 29. So 29 would be borrowing 5 bits. So 1, 2, 3, 4, 5. That leaves us 3 left over, and that allows us to represent what's 2 to the 3rd power? Well, it's 8. And 8 allows us to hold 6 and 5 efficiently. So that's how we can follow it up. So if you have any further questions about the magic bullet method, I'm more than happy to go over that with you again in class. And again, you'll see it in Net 125. So subnetting in IPv6 is way, way simpler than IPv4. We don't use class divisions because we don't have to. The octet structure is not there, obviously. We're using hexadecimal, and we're using an address space that's 4 times the length. So it supplies 18 quintillion IPv6 addresses in a single subnet. We don't really need it. Subnetting does let us manage the volume of IPv6 addresses, however. If we were to assign everything out individually, it would get really messy. So subnetting lets us block things off so that we can still have a manageable group of addresses. An IPv6 address is commonly written as 8 blocks of 4 hexadecimal characters each. The last 4 blocks are going to tell us the interface, so the 64 bits at the end. The first 4 are going to identify the network and serve as what's called the network prefix or global routing prefix. In the site prefix, the 4th hexadecimal block, it can be altered to create subnets. So if we have 8 blocks, that means that we've got first 4, second 4, third 4, and then the 4th 4. So the separation right before the subnet mask would normally kick in is going to be where we create our subnets. Now, a VLAN, virtual local area network, will group traffic together on a switch via the ports to which they are connected. And this allows us to make sure that the traffic on the switch is forced to go through a router. This limits traffic to a smaller broadcast domain. This is part of the efficiency we were talking about much earlier in the lecture. We use VLANs because we may occasionally need to isolate a connection with a heavy or unpredictable traffic pattern. We may also need to identify groups of devices where data should be given priority handling, part of what's called QoS. And we may also need to contain groups of devices relying on legacy protocols. These protocols may be otherwise incompatible with the majority of the network's traffic. They may also be congestive. They may cause loss of speed to more efficient protocols, so we kind of trim that out. We may also need to separate groups of users who need special security or network functions. We may need to separate out traffic that's coming in from a VPN. We can also configure temporary networks this way, especially for experimental stuff, sandboxing, if you will. And we can also reduce the cost of networking equipment in this way. Rather than having to have a dedicated switch for this particular type of traffic, we can just dedicate a certain number of ports to a VLAN. Now, an unmanaged switch is just plug and play, ready to go, has no assigned IP address, so it cannot be directly configured through a remote connection. A managed switch can be configured via command line or through a web-based management GUI. Traditionally has its own IP address, which means that you will have to count a host address for it. And VLANs can only be implemented through this type of switch. Once this type of switch is set up, however, you can then partition ports into groups and start creating these VLANs. So here we have a number of figures, and I'll just kind of go through each. I'll do the left column first and then the right column. Figure 817 shows us how some of these ports may be configured for different types of VLANs. One for voice, one for accounting, one for marketing, one for sales. So different groups within a company may have different VLANs assigned to keep their traffic sequestered. Figure 818 shows us a switch connecting to a simple LAN. So we have our LAN, switch, router combination. Figure 819 shows us a slightly different variation on this with a managed switch, meaning that each port set is partitioned into a different group. So we have VLAN 1, VLAN 2. If we consider that 819 and 820 are referring to the same group, then that means that the first block of 8 ports on VLAN 1, and as well as the first 6 ports on the third block, all of the ports highlighted in red, the second block of 8 16 go to VLAN 2, and then the last 4 in the third block. So we can see the red and blue highlighting. Those are just physical representations of the logical separations for those ports. Now, in order to incorporate this management, we use a new IEEE standard called 802.1q. This allows us to define what are called sub-interfaces. So this is going to allow us to set up how VLAN information appears in a frame and how it's interpreted by the switch. This is a tag that gets inserted between the source address and the Ethernet type. So the switch is going to add that to the frame, which when it arrives at the switch will then be interpreted. Now tags will travel until it reaches a router or the switch port connected to the destination device. If a frame is being routed to a new VLAN, it's kind of like when routing occurs with a MAC address. It gets peeled off and a new one gets added. Then once the frame reaches its final switch port, it will then be removed entirely. So here we see now 3 switches on a LAN with multiple VLANs. We have a router to a switch to a secondary switch, and they're able to funnel traffic into separate VLANs the same way. Now, when we set up a managed switch, these ports are configured either in what's called access mode or trunk mode. Access mode is used for connecting a single device or node. A trunk port allows us to funnel traffic among multiple VLANs, so this is usually from a switch-to-switch connection. The trunk is going to allow multiple logical VLANs to connect on a single physical interface. Trunking protocols will assign and interpret the VLAN tags we just spoke about, and most commonly they'll use what's called Cisco's VTP, or VLAN Trunking Protocol. It's the most popular VLAN tag exchange. It allows changes to VLAN databases to be done on one switch, which is called the stacked master, and that switch will then communicate with all other switches in the network using Cisco's CDP technology. CDP allows both discovery and declarations of changes to neighboring devices. So here we can see that we have a trunk port on this particular switch in order to pass traffic to multiple VLANs. So we can see if we're reading this correctly, excuse me, we've got the first 16 ports for VLAN 1, the second 16 going up to port 32 for VLAN 2, and then we've got 33 through 38 for our VLAN 1, and then port 39 is going to be our trunk port, which allows us to connect traffic to VLANs 1, 2, and 3. And you'll notice there are no ports dedicated to VLAN 3 on this switch, but the VLAN can still pass through it. So here we can see how the trunk lines are laid out in purple, going between the router and switches. And then we can see the access ports for each individual VLAN, allowing traffic to pass from one to the other. Now each VLAN is assigned its own subnet of IP addresses. We see in figure 826 the router interface configured to support all 3 subnets. If you look back to figure 822, you will see the 3 subnets divided, and at this point we can understand that the router is actually going to see 3 logical virtual LANs, so a logical representation of a physical connection hooked up to a single router port. Now there are a couple of different types of VLANs with which we will work. The default VLAN, which is pre-configured on a switch and traditionally includes all of your ports when you first set it up. You'll want to move away from that fairly quickly. The native VLAN, which receives all untagged frames from untagged ports. I don't like having a native VLAN if I don't have to. Untagged ports tend to be a very common way that people try and manipulate traffic. A data VLAN, which carries all of our user traffic. Management VLAN, which deals with administrative access. And voice over IP traffic through the voice VLAN. Now once created, we're going to maintain VLANs through the switch's internal firmware, so the iOS software. In this case, we're going to look at figure 827 on the right, and this is going to be the result of the show VLAN command on a Cisco switch. This is used to list the current VLANs as recognized by the switch. So we can see that we've got our default number 1, and then we've got VLANs 5, 13, 14, 16, etc., going all the way up to 107. So I have to assume that these are categorized by some numerical system that we don't quite get, but are grouped together. We can also see that there is one VLAN, VLAN 5, that is empty. There's a VLAN there that has nothing in it. So that can be used sometimes as what we call a honeypot or a temporary network, things like that. Now there are some common errors that we may run into. Maybe we have a port in the wrong mode. Switch ports are often connected to endpoints and are set up in access mode, but can be sometimes set up for trunking mode, and which will cause problems. We can also have an incorrect VLAN assignment. We just mistype, or maybe that there's a configuration error. We also can have what's called VLAN isolation, where we set things on a VLAN that's not connected to anything. So devices are assigned to a VLAN, or the ports rather are assigned to a VLAN that do not have connectivity to the rest of the network. VLAN hopping is one of the threats we have to be aware of, where an attacker can generate transmissions that appear to belong to a protected VLAN. This is usually through something like double tagging. The VLANs get crossed in order to access sensitive data or possibly inject harmful software. This can lead to what's called an XSS, cross-site scripting intrusion. There's ARP poisoning, a number of different ones like this. So when we're dealing with VLAN hopping, double tagging is probably the most common. This is where VLAN tags are stacked. The legitimate tag is pulled by the switch, and then the second illegitimate tag is revealed, which tricks the switch into forwarding the transmission onto a restricted VLAN without verifying its contents. There's also what's called switch spoofing, which when an attacker connects to a switch and tries to make the connection look as if it's a trunk line. Then that VLAN traffic from the hacker can come in and try and access VLANs throughout the network using the legitimate reproduction of data flows. There are some mitigations that we can use to try and cut down on VLAN hopping. Of course, as I said when we looked at the table there in the show VLAN command, don't use the default VLAN if you can avoid it. It's not great. You also want to change the native VLAN to an unused VLAN ID. What happened with VLAN number 5, right? Disable auto trunking on switches that don't need to support traffic from multiple VLANs. That's a pretty good idea. I don't tend to use auto trunking if I have to. I only set it for the ports that I know will need it. On switches that carry traffic from multiple VLANs, make sure that all ports are set as access ports or are directly disabled unless they're used as trunk ports. Some people are a little bit paranoid, like myself, and will set ports to access mode before shutting them down, just to be sure. Specify which VLANs are supported on each trunk instead of accepting a range of all VLANs. This is a common rookie mistake. You don't want to have a non-specified VLAN range. I would rather have a VLAN not be working and I have to troubleshoot it and make sure that I have assigned it manually than to have all VLAN traffic coming through. That's how that false router thing can come in, that second method we talked about for hopping. We also want to make sure we're using good physical security. A lot of us think about the internet as being this nebulous thing, but it does rely on hardware that sits in front of us. So if we don't, lock doors to a server closet or make sure that computer labs are closed or things like that, we're going to have people that take advantage of those vulnerabilities. So definitely watch yourself. Be as smart as I know you are. And that's it. We'll go ahead and go over the chapter summaries. We talk about our primary contact methods and whatnot. Of course, if you have any questions or concerns, you can always come by my office and see me, or you can email me at jearmke063@cfcc.edu. You can also send me a text or give me a call on my Google Voice number, 239-7814. Hopefully this has been an enlightening experience and has encouraged you to maybe do a little at-home experimentation. Something that you will learn very quickly is that most successful network technicians or people who really enjoy working with computers do their best to be able to experiment at home. And with the nature of virtual machines and things like that, it's not really even a cost-exclusive thing anymore. You can find, sometimes old switches if you want to play around with those, or just work in a virtual environment. And of course, if you're ever curious, we tend to have open labs and love to have people come in and experiment. So always ask. The way that you get better is to practice. So hopefully I will see you guys in open lab, or just come by the office and ask some questions. Have a great rest of your day, and I will catch you next class.